Okay, let's draw an energy diagram of the reaction that we have been talking about for the last few videos, the electrophilic aromatic substitution reaction. You should be able to draw a appropriate energy diagram given the amount of information about the mechanism that you already have. And so if we ignore the catalyst, this is a reaction that is how many steps? 2 steps, right? Number 1, the electrophile adds, forming a carbocation intermediate. And then step number 2, the proton is being pulled off or comes off the benzene ring, reforming the aromatic ring and giving the final product. So it's 2 steps. The first step is rate limiting step. So pause the video and draw yourself an energy diagram for this reaction, starting with benzene and an electrophile. Okay, let's see how you did. So we will start out with our reactants at a certain energy, and the reaction happens, and so it's assumed that it's going to go downhill, so we want to draw it up high enough energy that you can go down to a lower energy product. Then we will start out with benzene. And the electrophile, those are the reactants. And then we will go up to form a high energy intermediate. And we're doing that by reacting the benzene with the electrophile. And so we're leaving a positive charge here and adding the electrophile there, breaking that pi bond. And so here is the intermediate. Positive charge here and electrophile there, and the appropriate extra hydrogens that are on there, right? There's 1 hydrogen on every carbon, so just make sure that you are seeing that in your head. Then we go down to a lower energy product, final product, and that is now we have pulled off the H plus and reformed the double bond. And so here we are with the double bond back, electrophile having added, and then H plus. 2-step reaction. First step is the slow step. The second one is the fast step. So this is what you should be picturing when you're thinking about this 2-step reaction. And one way that we can reason out where this electrophile is going to add, it doesn't matter where it adds here, but what if we had a substituent on the ring already? Let's say we had a substituent over here. We'll put it M for a meta director, then that substituent is still there, and the substituent is still there. If what we have done is we've looked at that substituent and by resonance structures reasoned out where the electrophile would prefer to add. And so when we did a meta director, we ended up with positive charges and these ortho and para positions, saying, well, the only one left is the meta position for this positive charged electrophile to add to. But you can also reason it out by looking at the intermediate. And so this intermediate is a carbocation, and if anything that stabilizes a carbocation will make that intermediate lower energy and the reaction faster. So anything stabilizing the intermediate makes it lower energy and makes the reaction faster. So we could have drawn a whole bunch of resonance structures of the intermediate where the electrophile added meta and compared that to the stabilization if it added ortho, or compared it to the stabilization if it added para. And this is what your book does, and let's take a look at how your book compares the energies of the various positions where the electrophile could have added. So basically you have three different intermediates that could form in this reaction. Now that we have a group that's already on the ring, we could form an intermediate where the electrophile has added ortho, we can form an intermediate where the electrophile has added meta, and we can form an intermediate where the electrophile has added para. So there's three, now that we have a substituent on there, there's three different intermediates. So let me find the book here and have us look at what this means. Okay, so this is on page 500. We went through some reasoning that a hydroxy group is an ortho-para-director by drawing three resonance structures of the starting material. You can also reason that out by drawing intermediate or resonance structures of the intermediate. And so if it adds ortho, it forms this intermediate. If it adds meta, it forms this intermediate. And if it adds para, it forms this intermediate. And you should take some time to make sure that you understand how this makes sense. Okay? Then there's resonance structures. This intermediate, if it adds ortho, has four resonance structures stabilizing that positive charge. If it adds para, then it has four resonance structures stabilizing that positive charge. And if it adds meta, it only has three resonance structures that are stabilizing that positive charge. So think about it. This is the intermediate that we talked about, that we just drew on our energy diagram. And if this is an ortho-para-director, then it means that the intermediate is lower energy if it adds ortho and lower energy if it adds para. So that means the reaction is going faster forming the ortho and para products and slower forming the meta products because the intermediate is higher energy on the way to the meta product. And so you should make sure, I've talked through this very quickly, you should look at these these resonance structures and understand why there are four resonance structures when it has added ortho and para, and why there's only three when it adds meta. And that will help you to understand why, or this is another way of explaining how this hydroxy group is an ortho-para-director. It was a heck of a lot easier to explain it and a lot simpler to explain it by drawing three resonance structures of the reactant showing where the partial negative charge was on the ring and reasoning out that it was a better nucleophile in that position. But if we had a methyl group here, we could not explain it by resonance structures of the reactant because there is no resonance in a methyl group. There are no lone pairs, there's no pi bonds, there's no resonance if this was a methyl group. So our simple explanation of the starting material using three resonance structures instead of 11 resonance structures wouldn't work for a methyl. It works for everything else, and so you don't have to explain things. You don't have to explain the way the book has explained on page 499, this is page 500, 501, and 502. All of those are using between 9 and 11 resonance structures of the intermediate. But you do have to use this method to explain and understand why a methyl group is an orthoparadirector and why it's an activator. So we're going to flip to the previous page and take a look at the explanation for the methyl group right here being an orthoparadirector and an activator. So in the next video, we'll talk through this.